Hello, my name is Pranav Raj from Department of CSCAM. Today I am going to explain about distillation. Introduction to distillation. Distillation is a physical separation process that exploits differences in the vola- volatility of components in a liquid mixture. It is widely used in industries such as petroleum refining, pharmacies, and beverage production for purification and separation. The core idea involves heating a mixture to create vapor and then cooling that vapor to recover purified components. Distillation is especially effective when components have significantly different boiling points. This technique plays a vital role even in interdisciplinary fields like AI driven processes optimization in chemical plants. Now we are going to learn basic principles of phase equilibrium. Phase equilibrium describes the balance between liquid and vapor phase of a substance at a given temperature and pressure. Each component in a mixture exerts its own vapor pressure, which increases with temperature. When the total vapor pressure equals the external pressure, boiling occurs. More volatile components, lower boiling points, tend to concentrate in vapor phase. Understanding vapor liquid equilibrium is essential for designing efficient distillation systems. Types of distillation processes. Simple distillation separates liquids with a large boiling point difference, typically over 25 degrees Celsius. Fractional distillation uses a fractionating column to achieve a better separation of close boiling components. Steam distillation is used for heat sensitive organic compounds like essential oils. By introducing steam, vacuum distillation reduces pressure to lower boiling points, preventing thermal degradation. Steam distillation is used for heat sensitive organic compounds like essential oils. By introducing steam, vacuum distillation reduces pressure to lower boiling points, preventing thermal degradation. Azeotropic and extractive distillation handle mixtures that form constant boiling azeotropes by adding enterics. Fractionating column design and function. A fractionating column provides multiple vaporization condensation cycles to enhance separation efficiency. It contains trays or packing material that increases surface area for vapor liquid contact. Each theoretical plate represents one equilibrium stage where vapor and liquid phases each equilibrium. More plates allow for final separation, especially useful in refining crude oil into various fractions. Column height and diameter are designed based on throughput, desired purity, and pressure drop constants. The core idea involves heating a mixture to create vapor and then cooling that vapor to recover purified components. Distillation is especially effective when the components have significantly different boiling points. Raoult's law and ideal solutions. Raoult's law states that the partial vapor pressure of a component is proportional to its mole fraction in the liquid. For ideal solutions, the vapor pressure is the sum of individual component pressures. This law works well for chemically similar substances like benzene and toluene. Deviations from Raoult's law occur in non-ideal mixtures due to intermolecular forces. Understanding these behaviors helps predict how mixtures will behave during distillation. Simple distillation separates liquids with large boiling point differences, typically over 25 degrees Celsius. Steam distillation we used for heat sensitive organic compounds like oils introducing steam. McBay-Tail method, graphical design tool. The McBay-Tail method is a graphical technique to determine the number of theoretical stages in a distillation column. It uses equilibrium curves and operating lines plotted on y-axis diagram. The Q line represents the feed condition and intersects the operating lines. Each step between the operating line and equilibrium curve corresponds to one theoretical bit. This method simplifies column design for binary mixtures under steady state conditions. Notes deviations from Rhodes law occur in non-ideal mixtures due to intermolecular forces. Understanding these behaviors helps predict how mixtures will behave during distillation. Reflux ratio and its importance. Reflux is the portion of condensed vapor returned to the column to improve separation. The reflux ratio is the ratio of liquid returned to the column versus distillate collected. Higher reflux ratios increase purity but also raise energy consumption and operating costs. Minimum reflux ratio is the lowest value needed for feasible separation at infinite stages. Optimal reflux balances product quality, energy use, and economic efficiency. Energy considerations in distillation. Distillation is energy intensive due to the need for heating and cooling. Latent heat of vaporization must be supplied to convert liquid to vapor with the reboiler. Heat integration techniques like heat pumps can reduce energy demand significantly. Modern plants use pinch analysis to optimize heat exchanger networks around distillation units. Energy efficiency is a key focus in sustainable chemical process design. Industrial applications of distillation. Petroleum refineries use fractional distillation to separate crude oil into gasoline, diesel, kerosene, and other fractions. Beverage industry employs distillation to produce spirits like whiskey, vodka, and rum. Pharmaceutical companies purify active ingredients using vacuum or short path distillation. Air separation plants use cryogenic distillation to produce liquid oxygen and nitrogen. Chemical manufacturers apply distillation to recover solvents and purify reaction products. Challenges and limitations. Distillation struggles with mixtures that are azeotropes, where liquid and vapor compositions are identical. High energy consumption makes it less sustainable compared to membrane-based separation. Close boiling components require many stages and high reflux, increasing cost and complexity. Thermal degradation can occur in heat-sensitive materials like certain drugs or flavors. Alternative methods like pre-operation or absorption are sometimes preferred for specific applications. Role of Role of AI and machine learning in modern distillation. Machine learning models predict optimal operating conditions based on historical plant data. AI algorithms optimize reflux ratios and feed locations in real time to improve efficiency. Neural networks can model complex vapor liquid equilibria where traditional equations fall short. Digital twins of distillation columns simulate performance under varying inputs for training and control. Smart sensors and AI-driven analytics help detect falling or inefficiencies before they cause downtime. Case study: crude oil distillation unit. A typical crude distillation unit separates oil into naphtha, kerosene, diesel, and residue using a fractionating column. Preheating crude oil through heat exchangers improves energy efficiency before entering the furnace. The column operates at reduced pressure in the lower sections to prevent cracking of heavy molecules. Side streams withdraw products at different heights based on boiling ranges. Automation and AI-based control systems maintain product specifications despite feed variations. Future trends and innovations. Hybrid systems combine distillation with membranes or absorption for lower energy use. Modular and intelligent distillation units are being developed for decentralized production. Advanced materials like structured packing improve mass transfer and reduce column height. Renewable power distillation using solar or waste heat supports green chemistry goals. Integration with AI enables self-optimizing plants that adapt to market and environment demands. Thank you.